Have you ever stopped to think about how developers build the massive, complex software we use every single day? The apps on your phone, the OS on your computer. So much of it is built using this really powerful concept called object-oriented programming. And today we're going to pull back the curtain and demystify this fundamental blueprint for our digital world.
So here's our game plan. First, we'll tackle the big problem that OOP was invented to solve. Then we'll get into the right mindset, learning to think in objects. After that, we'll dive deep into its 4 foundational pillars, see how it's actually used to design software, and finally, we'll look at all the amazing benefits it brings to the table. Ready? Let's go.
All right, let's get right into it. To really get why object orientation was such a game changer, you have to understand the mess it was designed to clean up. See, as software started getting bigger and bigger, the old ways of building things they started to fall apart under their own weight. Okay, so the old school way of doing things basically saw software as a bunch of instructions or functions that operated on separate piles of data. You had your actions over here and your data way over there. Now, that's fine for simple stuff, but for big projects, it becomes a tangled web, a real plate of spaghetti code, where changing one little thing could break something totally unrelated. The object-oriented approach said, hold on, what if we bundle the data and the functions that use that data together into these neat little self-contained packages called objects? And that right there changed everything. And that brings us to the core aha moment of OOP. Let's model our software after things in the real world. It's a huge mental shift. Instead of thinking about abstract lines of code and procedures, developers started thinking about tangible things and how they talk to each other. And you know what? It turned out to be a way more intuitive and powerful way to handle complexity. So what even is an object in programming? Well, it's pretty simple, really. It's a bundle of 2 things, its state and its behavior. Its state is just the data that describes it. You can call them attributes or properties. And its behavior is just what it can do, the actions or methods it can perform. It has its own unique identity, totally separate from any other object. And this bicycle example is just perfect. A real bicycle has a state, right? Its current speed, what gear it's in, its color. It also has behaviors. It can brake, it can change gears. Well, in OOP, we'd create a bicycle object in our code that's a perfect mirror of this. It would hold its own data for speed and gear, and it would contain the functions or methods like apply brakes or change gear. The key insight here is that the object itself is in charge of its own stuff. Now, think about it. If you're going to build 1,000 bicycles, you don't just wing it every single time. No way. You use a blueprint. And in the world of OOP, that blueprint is called a class. A class is the template. It's what defines all the shared attributes and methods for all the objects of a certain type. And this is the crucial point. You design one single employee class. It defines properties like name and job title and methods like calculate pay. Then, from that one blueprint, you can stamp out as many individual employee objects as you need. Ada, Roche, James. Each one is a unique instance with its own specific data, but they all share the exact same structure and behavior defined by that employee class. It's all about designing once and reusing it over and over. Okay, so let's get into the secret sauce. How does this approach build such a strong, reliable foundation for software? The power of OOP really comes from 4 core principles. People often call them the 4 pillars. These are the rules of the game that make object-oriented design so incredibly effective. Now, these pillars are encapsulation, abstraction, inheritance, and polymorphism. I know it sounds like a mouthful, but trust me, the ideas behind them are super intuitive, and together, they let us build software that's modular, flexible, and just so much easier to wrap your head around. So let's break them down one by one. First up, encapsulation. This is that idea we talked about, bundling the data and the methods that work on that data into one neat little package. But it's more than just bundling. It's about creating a protective shield around the data. This makes our second pillar possible, abstraction. Abstraction is all about hiding the messy, complex reality and only showing the simple, essential parts. Think about driving a car. You see a simple steering wheel and pedals, you don't see all the complex machinery working under the hood. Encapsulation builds that complex engine, and abstraction designs the simple dashboard you use to control it. Next up is inheritance. And let me tell you, this is a massive game changer for being efficient. Inheritance lets a new class automatically get all the properties and methods of an existing one. So you might have a general vehicle class with things like speed and an accelerate method.
Then you can create more specific classes like car or motorcycle that inherit all that stuff from vehicle. A car can then add its own special details like number of doors without ever having to rewrite the basic vehicle code. It's all about reusing code so you don't have to write it over and over again.
And our final pillar is polymorphism, which literally just means many forms. This is the awesome ability for a single command to behave differently depending on the object it's sent to. So imagine you have different shape objects, a circle, a square, a triangle. You can just tell each of them, hey, draw yourself. The circle knows how to draw a circle, and the square knows how to draw a square. It's the same command, but each object responds in its own unique way. This makes your code incredibly flexible. Okay, so we've got these amazing principles, but how do developers actually use them to plan and build a real app? I mean, you don't just jump in and start writing code. It's a disciplined process of analysis and design, kind of like how an architect would meticulously plan a skyscraper before laying a single brick. The whole thing starts with what's called object-oriented analysis, or OOA. This is the what phase. What problem are we actually trying to solve? What does the user really need? Then that's followed by object-oriented design, or OOD, which is the how phase. This is where we create the detailed technical blueprint that's going to guide the entire project. It's all about making sure we build the right thing and that we build the thing right. One of the key tools for that analysis phase is something called a use case. The best way to think of it is just writing a short story about how a person will interact with the system. So for a library app, your user, or actor, might be the librarian, and a use case could be something like, add a new book to the catalog. It just captures what the user wants to do and exactly what the system has to do to make that happen. Now, to actually draw these software blueprints, developers need a common visual language so everybody's on the same page, and that language is UML, the Unified Modeling Language. Think of it like standardized sheet music for musicians. It's a set of symbols and diagrams that everyone understands, used to visualize and document all the different parts of a software system. And you can think of these different UML diagrams like the different drawings an architect makes for a building. A use case diagram, that's like the high-level site plan showing who uses the building and for what. A class diagram is like the detailed floor plan, showing all the rooms and how they're connected. And a sequence diagram is kind of like the electrical plan, showing how all the parts work together to make things happen. Each diagram gives you a different but absolutely essential view of the system. So, after all this planning and modeling and designing with these 4 pillars, what's the big payoff? Why do we go through all this trouble to think in objects? Well, the advantages are just massive. You get huge code reusability thanks to inheritance. You get modularity and better security because objects keep their data and logic to themselves. And all of this leads to software that's just way, way easier to maintain, debug, and grow over time. Honestly, it's the difference between building with high-quality interchangeable Lego bricks versus trying to glue together a bunch of random, mismatched junk. This quote really just nails it. With OOP, the way you talk about the problem in the early planning stages with objects, their properties, their actions, is the exact same way you talk about it when you're writing the final code. And it's this seamless journey from a real-world idea to a working piece of software that makes OOP so good at taming complexity. At the end of the day, by organizing our digital world in the same way we already see the physical one, as a collection of objects that have properties and can do things, object-oriented programming gives us this incredibly powerful and intuitive way to create. It's not just a set of rules for coders, it's a way of thinking that transforms complexity into clarity. The world is made of objects. So what will you build with them?